Hi, this is a talk on the pseudo-deterministic query complexity of NP search problems, and this voiceover is provided to you by Rahul Santhanam. It's based on joint work with Shafi Goldwasser, Russell Impagliazzo, and Tony and Pitasi. So the title of the talk probably is mostly familiar to all of you who are complexity theorists, except perhaps for the term pseudo-deterministic. The terms query complexity, NP search problems are probably quite familiar to you. The term NP search problems means something slightly different in the query world than in the standard complexity setting, where you might be more familiar with it. But I will explain what the title means as we go along. So here's the plan of the talk. I'm just going to introduce and motivate our results first, and then state them, the results as well as applications. Say something about the proofs and how they use proof complexity, and finally have a couple of open questions to tell you about. So pretty much sort of standard format for a talk of this kind. So to introduce the topic, let me try to motivate pseudo-determinism and the setting in which we study pseudo-determinism. So the main problem we consider is the find ones problem. That's a problem that we define in this paper. It is a very, very natural problem. The find ones problem is a search problem. You're given as input an n-bit string x for some n with at least n over 2 ones. In general, at least a constant fraction of ones. But just to make it concrete, let's say at least n over 2 ones. And what you need to do is to output an index I such that xi equals 1. So in this case, the index 12, I equals 12, satisfies xi equals 1, and that might be what we wish to output. So note that this is a search problem. You're given an input and you're asked to find some index satisfying a certain property. So it's a search problem. It's not a total search problem, but rather a promise search problem, because you're promised that the input x has n-bit string has at least n over 2 ones. It's a promise search problem. It's actually a search problem in NP in the query world. Right? So we need to define what sort of computational model studying this problem in. I mean, obviously, this problem is completely trivial in the standard complexity setting. We can just scan through the string and find the first one. So what sort of resource do we want to consider to make this problem interesting? So what we're going to be interested in is how many queries are required for a randomized algorithm to solve the search problem. So if you have a randomized algorithm that makes queries to your string and tries to output the index of a string, index of a 1, how many queries will be required? So it's a query problem. And in the query world, this problem is in NP in a sense, because what does NP mean? NP means that a witness can be verified efficiently. Right? In the query world, what efficient means is typically polylog n queries. So for an n-bit input, you have polylog n queries. And in fact, a solution to the search problem can be verified with just one query. I mean, so because the solution is an index over 1, so if you have a candidate solution I, you just query xi, and thereby you can verify whether xi is 1 or not. So that's the sense in which the find ones problem is a problem, is an NP search problem. But it's a promise search problem rather than a total one. It might surprise you that this problem, that there's something interesting you can say about it, because both in a deterministic and a randomized sense, this problem looks pretty trivial. Right? For a deterministic algorithm, well, it seems like there's nothing better you can do than just query the bits in order, and it's always possible that the one that you're looking for is so that you need to query n over 2 bits, and you haven't found a one because all of those happen to be 0, and so the first one in the string is the first bit that you haven't queried yet. So it's pretty easy to see that you would need to make NO2 plus 1 queries for a deterministic algorithm. And for a randomized algorithm, also this problem seems pretty trivial, right? I mean, since you're guaranteed that there are at least NO2 ones, you could just pick an index at random, check that it's a 1, and output if not. And if it's not a 1, then you repeat, you guess on the index at random and check it. And with high probability, this algorithm will succeed within a small number of steps. So this here's the algorithm that I just told you about. While xi not equal to 1, choose I and n uniformly at random and query xi. And the analysis of this algorithm is trivial. It succeeds with probably at least 1 minus epsilon after making log 1 or epsilon queries. So what sort of question can we ask about this problem that's non-trivial? Well, the question we ask is there a randomized algorithm that outputs a fixed index with high probability? Note that a deterministic algorithm solving this problem, the naive one that we spoke about, namely querying the bits in order, because it's deterministic, it's always going to output the same index. I mean, there's only one possible output of the algorithm, and that's going to be a fixed index. For a randomized algorithm, though, there are many possible outputs depending on the randomness. So is there a way in which randomness could be useful for a query algorithm without actually impacting the output in a significant way, so that the output really doesn't depend on the randomness, but the randomness helps in sort of saving on the number of queries? This is what pseudo-terms and the concept of pseudo-terms is all about. We want a fixed solution to the problem to be output with high probability. And the question is whether we can do much better than the trivial deterministic algorithm which queries indices in order. So here's a slide just discussing these three notions. Pseudo-deterministic is sort of intermediate between deterministic and randomized. Suppose we wish to solve the search problem S, and it's a very general notion, so we can consider it as we do here in the query setting, but it's been considered before in the standard complexity setting, setting of streaming algorithms, and so on. So deterministic algorithm, which is solving a search problem, it computes f of x, where f of x is the correct solution to S. A randomized algorithm with high probability computes a solution to S, but it could output different solutions on different computation paths. A pseudo-deterministic algorithm with high probability computes a fixed solution to S, outputs an f of x that solves S with high probability. And there's a couple of different notions of pseudo-determinism. There's bounded error notion and zero error notion, and this is really about what do you do on computation paths where you don't output the canonical answer. So this majority answer, f of x, we call canonical. And what about paths where you output a non-canonical answer? You could imagine a zero error pseudo-deterministic algorithm, which when it doesn't output f of x, just fails and says it doesn't know what the answer is. And in contrast, there's a bounded error algorithm, which could output some other sort of candidate solution, which might or might not be a correct solution when it's not f of x. So with high probability, it outputs a fixed output that solves a problem, but there could be other outputs on other computation paths. So these are the two standard notions. All our low bounds in this talk are going to be for bounded error pseudo-deterministic algorithms, which is clearly stronger than having a low bound for a zero error pseudo-deterministic algorithm. Okay, so just some historical background. This notion of pseudo-determinism, it's been implicit in some works in the past, but it was sort of explicitly defined by Gatt and Goldwasser, and it's been studied in a sequence of papers. There's several papers in the recent past studying this notion, but it's been studied mostly in the context of standard complexity setting, where you're measuring time or space, or circuit depth. It's also been studied in the setting of property testing, in the setting of streaming algorithms, in the setting of interactive proofs, and so forth. And it has also been studied in the setting of query complexity, but just in this one previous paper, that of Goldreich, Goldwasser, and Ron from 2013. And what they did was to show a linear low bound of the pseudo-deterministic query complexity for the problem of approximating the Hamming weight of a bit string. So if you're given a bit string x and you want a good approximation to the Hamming weight of x, There's a simple randomized algorithm which just generates random indices, and so it has a random sample, and it computes the weight of that sample, and that's with high probability by Chernoff bounds going to be a good approximation to the Hamming weight of the original bit string. So there's a randomized algorithm that makes few queries solving this problem. But pseudo-deterministically, it turns out to require linear number of queries, just as it requires a linear number of queries deterministically. So this already gives a strong separation between pseudo-deterministic query complexity and randomized query complexity. But it's not for a problem in FNP. If you want to verify whether the Hamming weight of a string is close to some value, it's not something you can do asking just a few queries. You need to ask a lot of queries deterministically in order to do that. So in this talk, our focus is on problems that are in FNP in the query world, problems where solutions can be verified with polylog n queries. And it turns out actually that the find once problem that we just defined is sort of canonical for this class, meaning that even though it's not a total search problem, it's a promised search problem. Any low bound for a problem in FNP translates to a low bound that's very similar for find once. And that's not very hard to prove. It's a structural result about complexity in the query world. So that's just to set up the talk and the background and the motivation. Now I'll tell you about the result. So I'm going to discuss in this talk 3 of the results in the paper. Theorem 1, which is our main theorem, is the low bound on find once. So the trivial algorithm for find once is a deterministic algorithm that asks each index in order to find a 1. And we've showed that pseudo-deterministically you can't do much better. You can't do more than quadratically better. Find once has pseudo-deterministic query complexity omega of square root n. And in fact, this bound is tight for quantum query algorithms. For quantum query algorithms, this low bound still works. You can define pseudo-terms for quantum query algorithms, and this low bound still works, and there's a matching upper bound up to polylogarithmic factors that follows from Grover's algorithm and binary search. A second theorem is an application of this first theorem and the techniques used to show that result. And it is a result about proof complexity. So there's a known proof system called random tree resolution. Tree resolution, standard proof system, together with kind of random axioms. And we show that the issue of this proof system is that unlike standard proposition proof systems, it's not efficiently verifiable. And we instead define a proof system called pseudo-deterministic tree resolution, which is efficiently verifiable. And we show that random tree resolution is in fact exponentially more powerful. And this proof just applies the main result of theorem 1. And while theorem 1 gives a separation between pseudo-deterministic query complexity and randomized query complexity, when randomized query complexity find once is constant and pseudo-deterministic query complexity omega square root n, theorem 3 shows that there's a setting in which, a very natural setting in which these complexities are the same essentially. So for any search problem S in distribution D, if you look at the average case complexity of the search problem over D, and specifically if you look at the zero or average case query complexity, it turns out that the deterministic average case query complexity of the search problem over any distribution D, the zero or pseudo-deterministic average case query complexity over D, and the zero or randomized average case query complexity over D are all equivalent, are all the same up to polylog n factors. And we also have a similar result, not as clean, for bounded error pseudo-deterministic algorithms. But I'm not going to say very much about theorems 2 and 3. I'm going to say a little bit more soon. But I'm going to focus mostly on the proof of theorem 1 in the remainder of the talk. So just to say a bit more about theorem 1, as I said, it's tight for quantum query algorithms. And just to signpost what's the proof going to look like. We're going to show an omega square root n low bound for another problem in FNP. So just remember that FNP always means in the query world. And this FNP problem that we show a low bound for is that for a certain sequence phi n of unsatisfiable CNFs that are expanding in a certain sense. Random CNFs work here. So this sequence doesn't need to be explicit. The problem is to find a falsified clause given an assignment of the variables of phi n. For each n, phi n is an n variables and has a linear number of clauses and has a property that every assignment falsifies a constant fraction of clauses. So the search problem here is very easily solvable in a randomized sense, just by guessing a random clause repeatedly and verifying that it's unsatisfied by the current assignment, by the given assignment. And we show that there's a omega squared and pseudo-deterministic low bound for this problem. And then we show how to translate this low bound for this FNP problem to a low bound for find ones. As I said before, find ones is canonical, that any low bound for an FNP problem translates to a similar one for find ones. Just a bit more about theorem 2. Random tree resolution is exponentially more powerful than pseudo-deterministic tree resolution. So here we apply our result for expanding CNFs, and our separation is for random CNFs. For random CNFs, it's known that they can be verified, that they can be proved with constant proof size and random tree resolution. There's a proof system that was defined by Bas, Kolodziejczyk, and Taupin, I believe. Pseudo-deterministic tree resolution is a constrained version of that, which is closer to what we usually think of as proof systems, where proofs are efficiently verifiable. And this sort of constraint turns out to weaken the proof system significantly, perhaps as one might expect, and now you're not able to prove random CNS efficiently anymore. You require exponential size and tree resolution to prove random CNS. And then there's theorem 3, as I mentioned, equivalence in the average case setting between deterministic, pseudo-deterministic, and randomized in a zero average case setting. And this is significant contrast to the worst case setting, where theorem 1 gives an exponential separation between the randomized and the pseudo-deterministic complexity. Okay, so now I'm going to say a bit about the proofs of our main results, and specifically about the proof of theorem 1. So what would be a first attempt to proving pseudo-deterministic query low bounds for a problem such as find ones? What we want to show is that any randomized query algorithm that outputs a fixed solution for find ones must make omega of square root n queries. Now, what's the standard way of showing low bounds? Well, one sort of natural thing to do is when you're trying to prove low bounds on randomized query algorithms is to use Yau's lemma. If you could show for some distribution D that there's a deterministic average case low bound over D, then that would translate to a randomized query low bound for the problem. However, this option isn't quite available to us because this approach doesn't distinguish between randomized and pseudo-deterministic query complexity. Note that by applying Yau's lemma in this way, you also show a low bound on the randomized query complexity. And we know that find ones has very efficient randomized query algorithms. So this sort of closes off one natural avenue of attack. What this tells us is that any approach we use for proving low bounds for find ones needs to take account of the semantic nature of pseudo-deterministic algorithms. Namely, that they always output a fixed solution with high probability. Yeah? So a randomized algorithm just outputs some solution. It could output different solutions in different computation paths. Pseudo-deterministic algorithms always output a fixed solution with high probability. And that's something we need to take advantage of in the proof in order to distinguish between randomized and pseudo-deterministic. And you also need to do a global analysis. You can't, so the low bound isn't going to work on average because on average, the average case sort of pseudo-deterministic query complexity could be much, much lower than the worst case pseudo-deterministic query complexity. The standard deterministic approach of querying bits in order actually, doesn't involve randomness at all, solves find ones efficiently on average over the uniform distribution. And theorem 3, which I sort of referred to earlier, where this actually generalizes this observation to every distribution. For every distribution, there's a pseudo-deterministic algorithm that solves find ones efficiently on average. What we end up doing is to use ideas from proof complexity, which is sort of cool, but mean, if you think about it more, is not too surprising because um, proof complexity low bounds are very closely tied um, to query complexity low bounds um, for total search problems. I mean, you might be aware that tree resolution, so like showing low bounds for tree resolution essentially corresponds to showing query complexity low bounds for the problem of finding like an unsatisfied clause in a formula. And similar kinds of connections between proof complexity and query complexity translate to other query classes, apart from the standard kind of deterministic or randomized query complexity. So this is in fact a very natural set of tools to try to use. And some sort of concrete complexity notions come in very useful here. So let f be a Boolean function on n bits. So the sensitivity S of f is defined as the maximum of all n bit inputs x of the number of coordinates to which f is sensitive on x. Namely, on any input x, consider which input bits to x would change the output of f if they were flipped. So that's what it means for f to be sensitive on x on the ith bit is if you flip the ith bit, then the value of f also flips. So that's the sensitivity at an input, and the sensitivity of S of f is just the maximum over all n-bit inputs of the sensitivity on x. So there's a standard notion in Boolean function sort of analysis, and used, for example, in the famous work of Nissan and Szegedi. There's also the degree d of f, also a very well-studied notion. The degree of the unique polynomial that represents a Boolean function f or the reals. And there's this very exciting recent result, Huang's theorem, which we're going to use, which actually relates, solving a long-standing open problem, relates d of f and s of f by showing that d of f is at most s of f squared. So what we're going to do is we're going to try to define these notions S and D for total search problems. And they can be defined in a natural way. I'm not going to go into it further, but you can define S of S to be the minimum sensitivity among all functions solving S, the search problem F, and D of S to be the minimum degree among all functions solving S. I mean, there's a sort of a technicality, which is that functions solving S will not be Boolean functions in general, but can easily generalize the notions of sensitivity and degree to function solving search problems, so that Huang's theorem still applies. And then going back to so that's this low bound here that we get. So that's just a short sort of high-level description of how the proof, the main result, goes. And in fact, our proof ideas for the low bound also go through for pseudo-deterministic quantum query complexity using some recent progress on extending Huang's theorem in that setting. And as I said, there's a matching upper bound. It can be shown using Grover's algorithm. And I'm going to mention a couple of very interesting questions that remain. One interesting question is, can we close the gap between the linear upper bound and the pseudo-deterministic query complexity defined ones, given by the trivial algorithm that queries each index in order, and the square root low bound that we obtain? And a very cool combinatorial question that's related and that we spent a lot of time on but didn't manage to solve is the following question. So consider colorings of the n cube of the hypercube and on bit strings of length n, where you have a certain notion of valid coloring. A valid coloring is a coloring of the vertices of the hypercube with n colors, such that each vertex x, and you're coloring all the vertices except the all zeros vertex, each vertex x is given a color I such that x sub I equals 1. So each vertex is colored by a 1 index of that vertex. So let's call such a coloring a valid coloring. And for any such coloring, valid coloring C, must there be a vertex that's near the middle layers of the hypercube that is having weight between n over 3 and 2n over 3, such that omega n of its neighbors on the level above, I mean, this is without loss to generality, we can also consider the level below instead, have a different color, right? So you're coloring all the vertices of the hypercube except the all zeros vertex. You're coloring each vertex by the index of a 1 of that vertex. And is the case that any such coloring will have the property that you can find a vertex such that all its neighbors above it or all its neighbors below it, that omega n of them have a different color. And that seems like it might be the case, but we don't know how to show it. And if this is the case, if you can show this, then it's quite easy to conclude from this the pseudo-deterministic query complexity of fine ones is omega n, and thereby get a tight bound. But as of now, we don't seem to have a low bound that's super logarithmic, so there's a massive gap between these two quantities. So actually, just to relate this to the proof techniques that I mentioned before, so we can think about this coloring, these valid colorings, and you can think about them as functions, and you can think about the sensitivity and the block sensitivity of these functions. And it turns out that using our techniques, you can bound the block sensitivity of these colorings by square root n from below. And that gives sort of a different proof of our main result. Because we can go through block sensitivity just as we go through sensitivity. If you don't know what block sensitivity is, don't worry about it. It's just a notion that's closely related to sensitivity that's been studied quite a bit in the past. So somehow the question is, well, so the low bound that we get for block sensitivity, does it also hold for sensitivity for such colorings? And in fact, can you get an omega n low bound rather than just omega square root n low bound? So a second question that's very interesting is to consider the communication complexity setting instead of query complexity. So we've looked at query complexity, and is it possible to show a similar exponential separation between pseudo-deterministic and randomized communication complexity for some FNP problem, FNP in the communication complexity world, where you can verify a solution by polylog n communication between the two players? Unlike in the query setting, you can actually separate pseudo-deterministic and deterministic communication complexity for an FNP problem. I didn't say this before, but for search problems, there's actually a polynomial relation between pseudo-deterministic and deterministic query complexity. But for communication complexity, this is no longer the case, because if you consider the inequality problem, where Alice is given x, an n-bit string, Bob is given y, you're promised that x and y differ, and you need to find an index in which they differ. You can solve this efficiently pseudo-deterministically by using binary search and the simple randomized communication protocol using hashing for checking if 2-bit strings are equal. So you can use this using a randomized protocol to find the first one in which these two strings differ. But it's easy to see using standard fooling set arguments that any deterministic protocol for solving the inequality problem requires omega n communication. So the communication complexity setting already, in terms of the relationship between pseudo-determinism and determinism, behaves differently from the query setting. And it remains an intrigue and open problem whether you can show a separation between pseudo-deterministic and randomized, and whether new techniques might be required for this. And this relates to all sorts of other cool problems such as circuit complexity low bounds, lifting, and so on. And please read our paper if you want to know more about this or more speculation about this. So that's all I have. You might have questions too, and I apologize for being unable to answer them right now, but please come along virtually speaking to the live talk at CCC and ask me then, if you so wish. Thanks.